jump into our next unit, which again, the first part of it is on exponents, okay, and exponential functions. It makes a ton of sense just to start with the properties. Again, these properties are covered in Algebra 1, but we haven't used them a whole lot this year. Yes, we've seen lots of things with exponents, but we haven't done order like operations that have terms that have exponents and how to handle those exponents. So this is, again, just a good entryway to that. It's a lot of simplifying today and applying these properties. And what we're going to do is we'll define the rule. I also like to explain why these rules work out, because chances are some of these rules you're going to be like, hey, product rule, do I add the exponents or multiply them? We're going to forget those when we're taking assessments, and that's okay. So how can we figure it out when we do forget it? That's going to be an extra thing I tag on to what we have in here. All right, so let's just start with actually talking about adding and subtracting monomials. Monomial meaning one term. So when we add terms that have exponents, the exponent does not change. Okay, this is us just combining like terms. So let's remind ourselves that combining like terms, for something to be considered a like term, they need to have the same exponent and same variable. And when terms have the same exponent and same variable, we can just add them together. It's just a counting game. We're just doing basic addition and subtraction. Okay, know that we do not change the variables and the exponents when we're adding these terms. Okay, only when we are doing other operations that we're going to get to in a second. Okay, so like 9x squared y minus 10x squared y. Okay, those are the exact same terms because the variables are the same, x and y, and the exponents on each of those variables are the exact same. So for me to add those together, I'm just thinking, what is 9 minus 10? That'd be negative 1. So I have negative 1x squared y. Or you can write it as negative x squared y. Exact same thing. Okay, exponent didn't change at all. Literally just counting. Okay, if I'm taking subtract 6w from 8w, that'd be 8w minus 6w. Again, those are like terms. Variable is w, exponent is 1. 8 minus 6 is 2w. All right, so that's something we've done already that we've been doing in almost every lesson we've had where we've had to combine like terms. But again, the reason I want to remind us about that is because the exponents aren't going to change there. But now as we start to do other operations with terms that do have exponents, they're going to start to change a little bit. Okay, so the first name, and the naming doesn't really matter. You might also hear this as like, let's kind of add some words to it. So when I say product rule, these are the same base. So same bases being multiplied. Okay, and this rule only applies if those bases are the same. So like if I have x times a times x times, or x to the power of a times x to the power of b, the base is x, exponents of a and b, we're going to add those. Okay, so we add the exponents. Okay, and again, just a couple examples here. If I have h2 times h to the 6th, this is where I'll kind of explain why this works. If I break down what each of these exponents mean, h squared means h times h. And if I multiply that by h to the 6th, so now I'm multiplying 6 more h's. So 1, 2, 3, 4, 5, 6. If I add or think about how many h's are being multiplied here, there's 8. So if I forget this rule, I can always break down what the exponents mean. Right? H squared, h times h. H to the 6th, h times h times h 6 times. In total gives me 8 h's. So that's h to the power of 8. So that reminds me, oh yeah, I have to add those exponents. Okay, so when you forget these, if you break down what the exponent means, you can usually figure it out. All right, on the second example here, really important that we see this as a very different problem than these like term problems. Okay, yes, I have a squared b and then a cubed b, but everything that's going on here, it's all multiplication. In the first set of parentheses, that's negative 2 times a squared times b. And then I have times 7 times a cubed times b. So everything there is being multiplied. So there's no adding or subtracting of like terms. This is just multiple problems or multiple simplifying of us having same bases being multiplied. Okay, so the number part will always just multiply the numbers. If the numbers are the same, we can change their exponents. But if I have a -2 times a 7, they don't need to be written next to each other for me to multiply those. Okay, I'm just going to multiply them right off the bat. That's -14. Okay, if this was like a -2 times another -2, you could say -2 squared, or we can always just get to the actual number of what that works out to be. It usually makes it a little more simple. Then I have these a squareds times a cubed. Well, using the product rule where same bases are being multiplied, I add those exponents. 2 plus 3 is 5, so I get a to the power of 5. And then b times b, that's b squared. Remember, if there's no exponent there, that exponent is really 1. Okay. Next property is called the power rule. This is when we have an exponent raised to another exponent. Okay, so when we have exponents raised to another exponent, this is where we're going to multiply them. Okay, so this would be x to the power of a times b. Here, could also write it as x equals ab. If I just write ab, that is implying multiplication. All right, so this is x squared cubed. Again, I'm going to use this example to kind of break down and pretend that I'm taking any sort of assessment. I forget this rule. If I have x squared and to the power of 3, I might be like, okay, do I multiply those exponents? Do I add or do I do something different? Well, again, I can break down what this means. Starting with x squared being cubed, well, that cubing is saying to take this base and multiply it by itself 3 times. So that's x squared times x squared again, right? This is representing x squared cubed. Well, now if I break each x squared down to get x times x times x times x times x times x, I see that there are 6 x's here. So how can I go from 2 to 3 to get to 6? By multiplying those exponents. Okay, so again, that's just me breaking down why this rule works out. And that is a great strategy for when you forget how to apply properties. And I actually like that idea for how we're going to deal with number 2. Because number 2 actually gets at another property in that when we have multiple terms inside parentheses all being raised to an exponent, like this -2 and the m to the 5th, both of the exponents are going to get multiplied. And a lot of students don't think of this -2 as having an exponent. Okay, so the first thing that I'm going to have us do here is let's write this out so I see the multiplication. So -2 times m to the 5th, all that is being squared, and then times m cubed. So really what is going to happen here, this exponent of 2 is going to multiply to the 5 to give us m to the 10th, but it also multiplies to the -2, okay, or the exponent on the -2. That -2 has an exponent of 1. And if I think about why, again, if I have -2 m to the 5th squared, well, that means -2 m to the 5th times another -2. Ran out of room. Times another -2 m. 2 is -2 squared, which is 4. And then m to the 5th times m to the 5th. I add those exponents to get m to the 10th. Okay, so this is positive 4 m to the 10th. And it's positive because of the -2 squared being -2 times -2. Okay, so now back to the actual expression here. I have -2 to the power of 2 times m to the power of 5. And then we still have to multiply this by m cubed. So -2 squared. And notice my use of parentheses there, right? If I don't have those parentheses, it's really easy to interpret that as positive 2 squared and then multiplied by -1. That's what your calculator will do if you do not add parentheses around it when you take it to the power of 2. But those parentheses tell me this is -2 times -2, which makes it 4. Then we already got, that should be m to the 10th, because that 5 times 2 is 10. And then adding the 3 gives me m to the power of 13. Okay, so there we're applying a couple different rules in one. And that's what your assignment's going to have. A lot of rules mixed together. So let's add just to this right here that every base raised to an exponent, let's say every base's exponent gets multiplied. Okay, so if I like x times y times z all to the power of 5, that exponent of 5 is going to multiply to the exponent on the x, the y, and the z. Okay, couple more. Next one being the quotient rule. This is where we have same bases being divided, so it's the opposite of the product rule. Okay, and with it being the opposite of our product rule, we're going to apply the opposite property for what we did with that product rule. So instead of adding the exponents now we're going to subtract them. Okay, so when we do the subtraction, sorry, this says same bases being divided. Yeah, same bases being divided. When this happens, it happens in the numerator. So if I have x to the a divided by x to the b, this is x to the a minus b, and all of that is over 1. Okay, so if we're going to apply the subtraction, know that the way we combine those bases happens in that numerator, and the denominator would be 1. And again, I've got a few different things I'm going to show us with this. We'll start with number 1 over here. First thing, when we have these numbers, because we have dealt with fractions, we just had a full unit on that, I want those number parts to be reduced down. So if I have 27 divided by 42, we can reduce that down by dividing a common factor. Calculators are really helpful for that. Where I can take 27 divided by 42, math enter, enter, and it reduces it down for me, being 9/14. So I could divide each of those numbers by 3. That's not an exponent property. That's more of a rational expression property. It's what we just tested on before we had our snow days here. All right, then we still have this x to the 5th divided by x. Now, what if we follow the rule, this would be 9 and then x to the power of 5 minus 1 all over 14. So I'm subtracting the exponent of 1 in the numerator, making it 9x to the power of 4 divided by 15. Now, another way to kind of think about this property is to actually treat it like a rational expression, what we just tested on. And so what I mean by that is if I have x to the 5th divided by x, yeah, go ahead. 14. Thank you. Okay, if I have x to the 5th divided by x, and again, if I break this all down, in my numerator, I have a bunch of x's, right? X times x times x times x 5 times. So really what's happening is we get 1x to divide out in my numerator and 1 to divide out in the denominator. So if I take 1 away from 5, that gives me x to the 4th. Okay, and I really like that way of thinking about this property when this is reversed, where my numerator might be x and the denominator is x to the 5th. Well, instead of me doing x to the power of 1 minus 5 and getting a negative exponent, I can just think about, well, 1x divides out in my numerator with 1x in the denominator. So if that 1x in the numerator divides out, I have a 1 there, and that'd be x to the 4th. Okay, so this property is more like a rational expression property than an exponent property. And essentially, I'm just factoring and canceling out common factors. All right, so number 2, and when we start to get mixed properties, just do one thing at a time, okay? Especially if you're like, man, I haven't done this in forever. Some of us might be thinking we haven't done this really ever at all, when that's probably not true, but I know it's been a while. The first property I'm noticing is I have this y squared then raised to the power of 2. So I'm going to multiply those exponents. My numerator becomes y to the 4th. I'm dividing by y to the 4th. Well, I don't need to apply this property to know that this is going to be 1, right? If I take y to the 4th minus 4, that's y to the power of 0. That's another property we need to add in here. Let's just remind ourselves of that. 4 minus 4 is y to the power of 0. What's anything to the power of 0? 1. This is a good explanation for why, right? Anything divided by itself is 1. Okay, so when you have an exponent to the power of 0, that will always be 1. Okay, whenever we have multiple properties and we see that exponent of 0, this should be really nice because we can just cross that thing off. It's 1, it goes away. Okay. Now this brings in the last property, and being negative exponents. This is one that students have the hardest time with. And the negative exponent, that name kind of explains it. What we're going to do with it, or how I think about this, is the negative exponent tells us to move the base. To numerator or denominator. Okay, so that negative exponent, think of it as being just like a, hey, I've got to move this base. Okay, it's going to move to either, if it starts in the numerator, it's going to move to the denominator, or vice versa. If it's in the denominator, I'm going to move it to my numerator. So think about this as x to the negative a over 1. So this negative exponent says, hey, this base needs to move. It's going to move to the denominator, and that's when I can make the exponent positive. So once we move it, the exponent now becomes positive. And so the opposite of this is if I have 1 over x to the negative a. If I have a negative exponent in the denominator, again, that negative exponent says, move that base. So it's going to go to the numerator, and that's when I can make it positive. Okay, so those negative exponents can be kind of tricky because of that. One quick reason why negative exponents work this way. We actually need a table for this. Let's say I have x and 2 to the power of x. Let's go 2, 1, 0, negative 1, and negative 2. Okay, so we know that if I have x being 2, 2 squared, that's 4. 2 to the power of 1, that's 2. And then 2 to the power of 0, we know is 1. Now, if we look at these y values I get by applying that exponent, and I think about how can I go from 4 to 2 to 1, what operation is happening here, I'm dividing by 2 each time, right? 4 divided by 2 is 2. 2 divided by 1, or excuse me, 2 divided by 2 is 1. So if that continues to where the exponents now become negative, and I get 2 to the power of negative 1, well, I'm taking that 1, which was the value I got from 2 to the power of 0, I'm dividing that by 2. 1 divided by 2 is 1/2. Okay, so that's kind of why we're getting this negative exponent rule as almost creating fractions, okay, or flipping our base is another way to think about what's happening here. And when I apply that one more time and get 2 to the power of negative 2, well, now I'm taking 1/2 and dividing that by 2. That makes this 1 over 2 squared, or 1/4. Okay, so that is 1 over 2 squared, or 1/4. This also helps us think about why anything to the power of 0 is 1. It all follows this pattern of taking our y values, or values we get by plugging in x, and dividing them by 2. So with exponents, there's 2 really important things here. no matter what I make this exponent, we will never get this to be 0. Okay, all I'm going to do is get really, really, really close to 0. We're going to explore how that affects our graph on Friday. Hey, Alexis Page, we need to pay attention, please. The other thing that happens with exponents is we'll never get this to be negative, right? So there's no exponent that I can plug in here to make the whole thing negative. All these y values will always be positive and will give us some value between 0 and really infinity, right? If the exponent gets bigger, it's going to just keep increasing. Okay. So let's work through these examples real quick. -5, first again, this is -5 times x to the -2. That exponent of -2 is not being applied to that -5. If need be, add an exponent of 1 to that -5 so we know they're separate. The only thing that needs simplified is we do not want negative exponents. So this is really -5 times 1 over x squared. That's what that negative exponent is telling me to take that base, move it to the denominator. Well, now if I multiply these terms, which we just tested on this, that becomes -5 times 1 in my numerator divided by x squared. You do not need to show this amount of steps for this. Okay, when I see -5x to the -2, I'm right away going to say, oh, that's -5 over x squared. Okay, I know that that negative exponent sends that term to the denominator, and then I make the exponent positive. But if you want to break it down as to what they mean and apply it individually, you can do that as well. All right, and last one, 4 divided by 8. That's 1/2. So let's reduce that down. So you can say 1k squared over 2k to the 5th. Again, this would be a really good example to where I'd say, oh, I've got k squared in my numerator, so I can cancel out with 2 in the denominator, leaving me with k cubed in that denominator. Well, if I just follow this rule, I'm going to get there as well. It just takes a little bit longer because I do 2 minus 5, since I have same bases being divided, telling me to subtract those exponents. So that's 1/2 k to the -3. So 1k to the -3 divided by 2. Negative exponent says, hey, take that base, move it to the denominator. So it becomes 1 over 2k cubed. Again, much easier way to think about this as a rational expression where I get 2k's to divide out in both that numerator and denominator, and it simplifies from there. Okay. The only thing that I did not get to, and this is kind of an extension for this power rule, let's add this up at the top just because we don't have a lot of room here, is if you have, let's say, x squared divided by y cubed all to the power of 3, this is the same thing as that power rule where every exponent here is going to get multiplied by 3. So I almost think about it as like the distribution property with exponents. Okay, so that 3 multiplies to the 2, making that x to the 6th. And that y also gets multiplied, making that y to the 9th. Okay, again, you can always write out what it means to cube something to really get a good idea as to how we get those terms there. Okay, not too bad. We got 25 minutes to now work on the assignment portion, which is on the back. There's a lot, but you're going to see the first like 20 go really quick. You're going to be able to do like number 1 in 2 seconds, number 2 in 5 seconds, and the bottom. So since you all have tomorrow to work on this, I'm hoping that we have some questions that we can come in tomorrow and say, hey, can I get an explanation as to why 26 works out to be 1 over j to the power of 3? So plan to have some questions when you come in tomorrow. All right, rest of the period is your time to get some work done.